This is an online map of global maritime traffic. At this very moment, more than 7,500 container ships are sailing around the world. And you know what's most surprising? If you looked inside the fuel tanks of almost any one of these giants, you wouldn't find regular diesel or gasoline. The fuel these ships run on is more like the asphalt you'd expect to see being laid on a road. It's so thick and heavy that at room temperature, it turns into a solid mass, something you could literally walk on. So why do these ships run not on high-quality fuel, but on what's basically asphalt? And how do container ships even manage to use this black sludge? Let's find out. It's hard to believe that people even thought of refueling ships with this thing. Heavy fuel oil looks less like something that came out of an oil pipeline and more like something scraped out of a bucket of road asphalt. At room temperature, around 68 degrees Fahrenheit, this stuff barely moves. Seriously, pour it in a bucket, turn the bucket upside down, and it won't exactly spill out. It'll creep out slowly, bit by bit. In terms of consistency, it's closer to thick tar or honey that's been sitting around for far too long. When it's cold, it's almost impossible to use properly. You can't pump it through the system, push it through pipes, or spray it through injectors. It just clogs everything. If fuel reaches the engine in that state, the engine won't keep running for long, and nothing good comes after that. So heating it isn't optional, it's essential. To get the fuel moving through the system at all, it's heated to about 122 degrees Fahrenheit. But even then, it's still too thick for the engine to use efficiently. That's why before it's fed into the cylinders, the temperature's raised even further, to around 248 to 284 degrees Fahrenheit. Only then does it become fluid enough to be injected and burned properly. And that raises an obvious question: how practical is it to use a fuel like this at all? A container ship isn't just an engine inside a hull, it's an entire fuel handling system, with heating required at almost every stage. Part of the ship's energy is constantly being spent just to keep the fuel in a usable state. If it cools down, the whole system can grind to a halt. The fuel thickens, stops flowing properly, and the ship effectively loses propulsion. So where does this strange substance come from? This fuel that even a container ship has trouble digesting? To answer that, we have to look inside an oil refinery. There's no way around it. And that's where things get interesting. The whole process starts with one murky raw material, and the goal is to squeeze out everything that can be used. Crude oil isn't just a liquid, it's a messy mixture of all kinds of components. Light ones, heavy ones, and plenty of things somewhere in between. The oil is heated, and at a certain point, different parts of it begin to evaporate, each at its own temperature. The lighter components rise first. They're volatile, mobile, and most importantly, valuable. They're collected at the top. The main product we get from these lighter fractions is gasoline. We all know how important that is. Then there's kerosene, or jet fuel, which keeps aircraft in the air. After that comes diesel. These are familiar, useful products, fluid, relatively clean, and expensive. But at the bottom, something else is left behind. The part that didn't want to evaporate, or couldn't. Heavy, thick, dark. Essentially, it's what remains after crude oil has been taken apart. But even this isn't something you can simply pour into a container ship's engine. This black sludge has to be cleaned of water and impurities. Then it's processed through units that remove part of the sulfur, then blended with other fractions to bring it to the right viscosity and performance level. In other words, a raw residue is turned into a tuned fuel, one that can be pumped, heated, and burned steadily in a marine engine without destroying it in the first few voyages. But even then, using this fuel still comes with serious problems. For example, there's this stuff with a very odd name, cat fines. Sounds harmless, right? Just dust? But in fact, it's one of a marine engine's worst enemies. So where does it come from? At oil refineries, when they're trying to squeeze as much gasoline and other light products out of crude oil as possible, they use a process called catalytic cracking. In simple terms, they add special particles to a hot mixture to speed up the breaking of heavy molecules into lighter ones. These particles are tiny bits of aluminum and silicon. And that's where the problem starts. Some of those particles end up in the residue, the heavy leftovers that are later used to make fuel for container ships. On their own, they're almost invisible. But in terms of hardness, they're basically an abrasive. Imagine extremely rough sandpaper, except it's inside the engine. If those particles slip through the filters and make it into the cylinders, they begin slowly but relentlessly wearing away the metal. Not instantly, of course, but after just a couple of weeks of normal operation, they can damage an engine so badly that repairs cost a fortune. That's why things on board are far more complicated than they might seem. Before the fuel ever reaches the engine, it's run through special centrifuges for a long time. These machines spin at insane speeds and literally knock everything unwanted out of the fuel oil. Solid particles, water, dirt, and other impurities. The engineers monitor the process almost nonstop. They clean, check, and clean again. And yes, the sludge that builds up in there looks, let's just say, unpleasant. But there's another issue tied to the heavy fuel used by container ships. When fuel oil burns, it releases sulfur oxides and nitrogen oxides into the air. In areas with heavy shipping traffic, that affects air quality right away. Acid rain, respiratory problems, the whole package. On top of that, combustion produces a lot of soot and fine particles. That black smoke coming out of the funnel isn't an exaggeration. It settles wherever the wind carries it, including on Arctic ice. The white surface gets darker, absorbs more heat, and starts melting faster. After learning all of these nasty things, we finally arrive at the main and most obvious question: why do shipping companies bother with expensive, round-the-clock heating systems at all when they could just use normal, cleaner diesel? The answer, as with so many global industries, is very simple. It all comes down to money. In the harsh world of ocean freight, the price of the fuel in the tank decides almost everything. The scale of real daily fuel consumption on a modern container ship is hard for an ordinary person to wrap their head around. A typical ocean-faring giant carrying up to 20,000 steel containers on deck can easily burn 150 to 250 tons of fuel in a single day at sea. Yes, you heard that right. That's the equivalent of several full railway tank cars of thick, heavy fuel oil. The wholesale price gap between dirty, heavy fuel oil and cleaner, safer marine diesel is enormous. It can easily reach $300 to $400 per ton. So let's do the math. If a ship burns an average of 200 tons a day, switching to cleaner fuel would instantly raise a shipping company's operating costs by $60,000 to $80,000 per day for just one vessel. A standard commercial voyage from a major Chinese port to northern Europe takes roughly 30 to 40 days of continuous sailing. Using the proper cleaner fuel would make that one-way trip alone $2.5 to $3 million more expensive. Across an entire year and across a giant fleet of hundreds of ships, that turns into billions of dollars. And you know what's the important part? If shipping companies were forced to use expensive diesel, the cost of transporting a new TV, a pair of sneakers, or even a basic t-shirt by sea would rise dramatically, and ordinary consumers would feel it in their wallets. So ultimately, the affordability of goods shipped from the other side of the planet comes down to one little-known fact: that huge marine engines can burn toxic leftovers from oil refining. You could say modern global trade is built on extremely cheap heavy fuel oil. All right, the price argument's clear enough. A cheap resource will always find a use, but money isn't the only factor. There's another, much more practical reason why heavy fuel oil became so common on huge ships. If you look inside a container ship, what you find isn't really an engine in the everyday sense of the word. It's a monster, a machine as big as a house, literally about 4 stories tall. And the way it works is honestly strange. The crankshaft turns slowly, very slowly, around 80 to 100 revolutions per minute. For comparison, the engine in your car, even while idling in traffic, runs at least 10 times faster. But here, there's no hurry at all. This kind of engine doesn't need a sharp, explosive burst like gasoline provides. It doesn't care about quick, short pulses. What it needs is a long, heavy push, the kind that keeps pressing, pulling, and driving forward. And oddly enough, heavy fuel oil fits that job perfectly. Because of its structure, it burns more slowly than lighter fuels. The result is steady, powerful pressure. Exactly what you need to turn a giant propeller. There's another factor people often forget: energy density. The molecules in heavy fuel oil are packed very tightly. In the same amount of space, it produces more heat than lighter fuels. The difference isn't huge, but it matters, roughly 10%. And at sea, things like that stop being minor details very quickly. Imagine a ship sailing for weeks with nothing but water in every direction, and the nearest port who knows how far away. Every extra percentage point of efficiency means more miles of range, or to put it bluntly, a better chance of not ending up in the middle of the ocean with empty tanks. Paints an interesting picture. What looks like a dirty leftover, almost a waste product, actually turns out to be well suited for long, steady operation. Not perfect, of course, but surprisingly fit for the job. There's another reason the whole world has clung to heavy fuel oil for so long, and it's much less obvious. Ships aren't built overnight. The vessels being launched today were usually designed 5, sometimes even 10 years ago, and they're not built for just a couple of trips. They're designed to work for decades, around 25 to 30 years if everything goes according to plan. Over time, engineers have built entire systems around one specific fuel, namely heavy fuel oil. The heaters, separators, filters, pumps, none of that equipment is truly universal. It's designed for one job. So, if you take an existing ship and try to switch it to something else, it gets expensive, very much so. In some cases, it's easier to build a new ship than to retrofit the old one. But honestly, the ships themselves are only part of the problem. Over several decades, a whole global infrastructure has grown around this fuel. Massive storage tanks and ports, millions of tons of heavy fuel oil, dedicated bunker barges whose only job is to refuel ships with this thick, heavy fuel. There are also people who know how to handle it and understand all the little technical details. This isn't just one warehouse and a couple of cranes, it's an entire system with enormous amounts of money sunk into it. And that raises the obvious question, can you simply replace all of it? In fact, no, you can't. You can't just snap your fingers and switch tens of thousands of ships to hydrogen or, say, batteries overnight. This infrastructure was built over decades. Loans were taken out to finance it, and it still has to pay for itself. As long as there's cheap, heavy fuel oil sitting in storage tanks, it's going to be used. The reality is pretty down to earth. There's another layer to this too, less visible but just as important: rules, standards, and habits. The entire industry has been operating under a well-established system for a long time. Mechanics know how to maintain these fuel systems. Insurance companies understand the risks. Everything has been calculated, written down, tested, and checked. And that feeling of predictability holds the industry in place almost as firmly as an anchor. Shipping in general doesn't like sudden changes. New technologies don't impress anyone just by being new. As long as the old systems still work and haven't been banned, they'll be used right up to the limit. Yes, heavy fuel oil is dirty, inconvenient, and problematic, but it's cheap and everyone knows how to work with it. Still, despite all its advantages, heavy fuel oil is gradually losing ground. Not suddenly, not with dramatic everything banned tomorrow headlines, but the shift is noticeable. Lawmakers are tightening regulations. One trigger goes back to 2007 with the MS Explorer situation. The ship was navigating icy waters when it struck a submerged iceberg. The ice literally tore through the hull and water started flooding the compartments rapidly. People were evacuated, but the ship sank. Technically, it wasn't classified as an environmental disaster. There wasn't a massive oil slick, but that incident served as a warning. If even a relatively small cruise ship can vanish in a matter of hours in these conditions, what would happen to a larger vessel carrying heavy fuel oil? As a result, heavy fuel oil was banned in Antarctic waters. By 2024, new restrictions were introduced, gradually phasing out heavy fuel use in the Arctic as well. Why were the rules so tough? In icy water, heavy fuel oil quickly thickens into a sticky, almost solid mass. It stops flowing, won't evaporate, and then it gets worse. Mixes with the ice, clinging to chunks and freezing into them for years, or even decades. Cleaning it up is extremely difficult. Standard methods used in warmer seas don't work. Pumps can't handle the thickened sludge. Skimming from the surface is a challenge, and the results are mediocre anyway. The pollution lingers, slowly poisoning fish, birds, and marine life. And the Arctic matters a lot. It defines global weather patterns, so any disturbance can have effects for miles beyond its borders. That's why restrictions there are just one of the steps, not the final solution. Already stricter rules exist in areas like the North Sea, the Baltic, and along the US and Canadian coasts. In those regions, ships switch to cleaner fuel in advance. And that made me wonder, why is all the focus on cold water? Does heavy fuel behave differently in warm seas? Well, not exactly. Warm waters have their own problems, often just as severe. Take the 2020 incident off Mauritius, for example. Japanese bulk carrier MV Wakashio ran aground and waves broke it apart. The ship was mostly empty, only carrying ore, but its fuel tank still held around 4,000 tons of heavy fuel oil, a standard amount for such voyages. When the hull cracked, about 1,000 tons spilled into the water, right into the lagoon. What happened next caught everyone completely off guard. A few days later, the scene had turned horrifying. This wasn't the usual rainbow sheen you see on the water in the news. The heavy fuel oil came back in thick clumps. It smothered the coral, seeped into the mangrove roots, and coated birds and turtles. The water had literally become thick and dark. Cleaning it up was far more difficult than anyone had hoped. Regular pumps just couldn't handle it. They kept clogging and breaking because the substance was so thick, almost like chewing gum. In the end, people had to make do with whatever was on hand. Buckets, shovels, and some homemade tools. They stood in that sludge, scooping out the oil by hand. The damage, of course, didn't disappear overnight. Coral suffocated under the thick layer, deprived of light and oxygen. Mangrove forests were devastated too. Cleaning them completely is nearly impossible without further harming the plants. And this, by the way, is the basis for the life of many marine species. So the heavy fuel problem isn't limited to cold regions. In warm seas, it can be just as disastrous, though the disaster looks different. But there is a glimmer of hope for those worried about the risks of shipping fuel. We're living in an interesting period, almost a kind of era shift, when ships moved from sails to coal. The major players are already making moves. Companies like Maersk and CMA CGM are investing huge amounts into new vessels designed to run without heavy fuel oil. We're talking billions. And this isn't just flashy marketing. These ships are actually being built. Of course, as usual, no perfect solution has emerged yet. Every option comes with its own challenges, sometimes tricky ones. The first contender is liquefied natural gas, or LNG. On paper, it looks very promising. Almost no sulfur emissions, and CO2 emissions are roughly 25% lower. There are even container ships already running on LNG. Take CMA CGM's Jacques Sade, for example. This ship can carry 23,000 containers and stretches nearly 1,300 feet in length. Most importantly, it runs on LNG, thanks to a unique 657,000 cubic foot cryogenic tank on board that stores the gas at minus 258 degrees Fahrenheit. Plus, the infrastructure to use this kind of fuel is already partly in place, and the technology's been known for a long time. In theory, you could just switch over, but there's one catch, and it's a big one. LNG is made up of about 85 to 90% methane, and using methane comes with what's called a methane slip. It sounds weird, but the idea is simple. Not all the gas burns inside the engine. Some of it just escapes into the exhaust. Methane is far more potent as a greenhouse gas than CO2. In the short term, it warms the atmosphere many times faster. So we end up in an awkward spot. On one hand, LNG is cleaner and feels like progress. On the other, if the leaks are significant, it could actually make things worse. We were trying to make things better, but in the end, it all went terribly wrong. There's another contender to replace heavy fuel oil in container ships' tanks, and it's drawing a lot more attention. We're talking about so-called green methanol. It has a pretty nice property. If there's ever a spill, it doesn't turn the ocean into a sticky nightmare. No black streak stretching for miles. Methanol simply dissolves in water. Not completely, of course, but the damage is nothing compared to what heavy fuel oil does. Plus, if it's produced from biomass, or say by capturing carbon directly from the air and using it in production, the fuel ends up almost carbon neutral. Sounds like a solid plan, right? But here's where the downside comes in. Methanol has a lower energy density for the same volume, roughly less than half that of heavy fuel oil. And that's a big deal. It means a ship needs far more fuel to cover the same distance. And where do you store it? The tanks have to get much bigger. That's when the hard math comes into play. Every cubic foot assigned to fuel is space taken away from cargo. Fewer containers mean less profit. It's simple economics. Still, companies like Maersk are seriously betting on it, backing their words with actual contracts and new vessels. Take the Ane Maersk, for example, one of the first truly massive container ships in the world running on green methanol. It can carry 16,000 containers, which is no small feat. To make the new fuel work efficiently, engineers had to completely rethink the ship's layout, moving the bridge and crew quarters all the way to the bow. This freed up room for enormous methanol tanks in the center of the hull while keeping the ship's huge cargo capacity without turning it into a floating fuel depot. And then there's another option which many call the boldest and also the most controversial choice: liquid ammonia. Basically, it's a completely carbon-free fuel. That's its biggest advantage. If everything goes perfectly, burning it produces nothing but ordinary water vapor and nitrogen, the same gas that makes up most of the air around us. For climate scientists, it's practically a dream. Zero carbon emissions. But as you might expect, even though it sounds amazing, there are still some catches. Ammonia is toxic. Not just unpleasant, it's genuinely life-threatening. Even minor leaks can be fatal. This gas severely irritates and damages the respiratory system. Now imagine this situation at sea. Closed compartments, long corridors, an engine running deep inside the ship, a small failure in the supply system, and the crew has very little time to react. These are not risks you can shrug off. That's why engineers basically have to reinvent the entire safety system. Double pipes, constant monitoring, thousands of sensors tracking every anomaly. None of this is optional. It's an essential part of the system. Without it, carrying ammonia is simply impossible. And that's not even the last challenge. Producing green ammonia is still expensive, far more than conventional heavy fuels like residual fuel oil. And here comes the simple everyday question: who's going to pay for it? As usual, the not-so-pleasant answer is that the final bill ends up with the consumer through higher shipping costs and ultimately higher prices for goods. Is there something more efficient, yet less dangerous? Well, one option is nuclear energy. Imagine a container ship powered by a nuclear reactor. It could operate for 10 to 15 years without refueling, produces almost no emissions, and isn't affected by fuel prices. Safety, of course, is a whole other concern, but in general, modern nuclear plants are considered some of the most tightly controlled sources of energy. Moreover, the technology is caught up. Companies like Core Power and TerraPower are betting on small modular reactors, compact units that can be adapted for ships. This includes liquid salt reactors. They run at low pressure, and in an emergency, the fuel simply solidifies instead of dispersing. Are there real examples? Yes, the Sevmorpet, a nuclear cargo vessel, has been sailing for decades, proving that it's feasible. So why isn't the ocean full of ships like this? First, cost and complexity. Ships like the Sevmorpet are expensive and require meticulous maintenance. In most waters, operating them often seems too demanding compared to conventional vessels. Second, the main barrier isn't the technology, it's the regulations. Most ports simply aren't ready to accept civilian ships with nuclear reactors. There are no standards, no infrastructure, and no appetite for taking on the risk. Every vessel has its own protocols, inspections, and escorts. Any fuel savings quickly vanish in red tape. In the end, it comes down to this. The technology's already there, and some working examples exist, yet widespread adoption hasn't happened yet. For the time being, thick, heavy fuel oil is still the go-to choice.